Today we're starting Unit 3A, which focuses on exponent rules and sequences. And what kind of ties these two things together are different patterns we can find with numbers. So this first day's lesson is focusing on finding some of these patterns. So if we go way back to when you first learned about multiplication, it was probably introduced to you as some form of repeated addition. So let's try to remember how we started with this. So if you had 5 plus 5 plus 5 plus 5 plus 5 plus 5, an easier way you realized to write this when you learned about multiplication was that you had 5 and you were adding it 1, 2, 3, 4, 5, 6 times. And so a shorthand way of writing that repeated addition was 5 times 6. Well, number 2, again, the number we're adding repeatedly is the 7, and in this case we're adding it 1, 2, 3, 4 times. Okay, for number 3, it doesn't matter that it's a decimal, it works the same way. So we're adding 2.4, and we're adding this one 1, 2, 3 times. And then for problem 4, we're adding a 2, and we're adding it 1, 2, 3, 4, 5 times. So this is all that multiplication is. It's just repeated addition. So now we're going to try to do verbal phrases into multiplication setups as well. So it says represent the following situations using multiplication for repeated addition. So if we were to add together 8 fours, and if you're not sure how to start this, you could always try to actually just write it out. So 8 fours would look like 4 plus 4 plus 4, all the way until we got to 8 of them. So the number that we're repeatedly adding is the 4, and the number of times we're adding it is 8 times. For number 6, it says add together in threes. Well, if we're adding together in threes, we don't know how many threes we're adding together. So this one literally would go on forever and ever and ever and ever for however long n is. We don't know. So the number that we're repeatedly adding is a 3, and we have no idea how many times we're going to do that. So we use a variable in its place. For number 7, it says start with 20. So now we're adding a starting value. This kind of ties back to how we view the y-intercept back when we did linear functions. So we're going to start with 20, and then we're going to add 10 5 times. Okay, so again, what the number I'm adding is 10 over and over and over again. This time it's specifically 5 times. I'm going to try to squish that in there. So this is the expanded form of this situation, and then we're going to try to represent it with the multiplication instead. So the number that we're adding is 10, and the number of times we're adding it is 5 times. And so that's a much faster way to get to that answer. All right, with number 8, we're going to start with 2, and we're going to add 7 3 times. All right, and so the faster way to write this would be 2, and then the number we're adding multiple times is a 7, and the number of times we're adding it is 3 times. All right, number 9, start with 50, and then add 6 n times. So this is another one of those where we're adding 6, adding 6, adding 6, and we could add for all of time. We don't know how long it's going to go, so we just use the variable n. So start with 50, we're adding 6 n times. And you don't have to write the parentheses if it's a variable. If you want to be consistent with our previous problems, we can, but that's optional if it's a variable. Alright, so let's fill in the blank here. It says we can use blank to shorten how you represent a repeated addition. And the answer to that will be yes, multiplication. Okay, so we all know that if we can do stuff with addition, we can do stuff with subtraction, but usually subtraction's a little bit trickier for most of us. So it says, does it work the same for repeated subtraction? Yes. So now let's give that a shot. So here they want us to start with 0 and then subtract 3 2 times. So they want me to subtract 3 2 times. So how can I write this with multiplication? Well, I'm starting with 0, the number I'm subtracting is 3, and the number of times I'm subtracting it is 2. And so that would be a faster way to do that, although that one's not very complicated to begin with. Number 12 says start with 80 and subtract 5 10 times. Now, I didn't expand it back up here. I probably could have actually. It's kind of bothering me that I didn't just add 8 4s. Sorry, I'm gonna be a little crazy right now and just fix this. The teacher in me just wants to do it right. So 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. 1, 2, 3, 4, 5, 6, 7. One more. And so then we wrote that 4 8 times. All right. And now I'm going to actually expand it down here. They want me to subtract 5 10 times. Oh boy. Okay, so it's on a problem like this that you really start to appreciate what multiplication allows us to do in a much more efficient way. So we can rewrite this one as 80, and then the number that we're subtracting is 5, and the number of times we're subtracting it is 10 times. All right, for number 13, it says start with 10 and subtract 4 8 times. So start with 10, and then we're going to subtract 4 8 times. 2, 3, 4, 5, 6, 7, 8. All right, so we're starting with 10, and we're subtracting 4. The number of times we're doing that is 8. All right, so hopefully this first page isn't too crazy. Usually we're pretty okay with understanding this connection between addition and multiplication. It's when we go to the next part that things get a little bit more confusing. So we're going to be doing a lot with exponents in this unit. That's a big focus because we're starting to look at exponential functions. And so we have to review these rules with exponents at the beginning of this unit before we can really do much else. So just remember that when we talk about exponents, there's two parts. There's the base number and the exponent number. Okay, so just like on the previous page, how one number told us the number we were using and the other number told us how many times we were adding or subtracting that number, this is similar, but just the exponent is telling us how many times we multiply that base number. Okay, so look for the following examples. Or at the following. They're right here. You don't have to look for them. So 3 to the 4th means that 3 is the number we're using, and 4 times is the number of times we're multiplying. And then we can actually evaluate if it's a base number. So then 2 to the 5th is 2 being multiplied 5 times, which is simply 32. All right, so on number 14, the number we're multiplying is a 5. And the number of times we're multiplying it is 4 times. So that would be 5 to the 4th power. On number 15, what we're multiplying is a 7, and the number of times we're multiplying it is 3 times. Again, it doesn't matter if it's a decimal or a fraction or a plain old integer, it's going to work the same way. Now, when I do have decimals, sometimes it might help to put them in parentheses just to make sure it's clear what you're raising to a power. So in this case, 2.7 is our base, and our power, our exponent, is going to be a 2. All right, for this last one, we have a base of 9, and we're multiplying it 1, 2, 3, 4, 5, 6 times. Okay, moving on. So now we're going from words. These are usually a little bit harder, so I like to do the step of kind of writing it out first and then condensing it. So multiply together 8 4s. So that means we have 4 being multiplied 8 times, and this time I'm just going to write it out. Remember, we had adding it 8 times on the previous page. 1, 2, 3, 4, 5, 6, 7, and 8. And so that means that the base is that number that's being repeatedly multiplied, and we know the number of times for this particular example is 8 times. The next one says multiply together in threes. So again, on the previous page we were adding, now we're multiplying, and it's just going to keep going. We don't know how many times. So the base is a 3. In this case, the power or exponent is n. We don't know how many times we're going to end up multiplying. And I got my colors backwards, but it's okay. We'll just switch up green and blue. So here we're going to start with 20. And this time we're going to multiply by 10 5 times. So then multiply by 10, done. Okay, so the setup would be 20, and then we're multiplying by a base of 10, so times 10, and then the number of times we're multiplying it by is 5 times. Okay. Sometimes you may also see this written with parentheses, and that's also fine with me. In fact, when we get into most of the exponential problems, I'll switch to parentheses just because we'll get decimals sometimes, and the dot multiplying when you have decimal numbers is quite confusing. But either way is fine for now. All right, number 21, start with 2 and multiply by 7 3 times. Alright, so we're starting with a 2, we're multiplying by a base of 7, and the number of times we're doing that is 3 times. Okay, start with 50. Whoa, that's a really bad 5. Let's try that again. Start with 50 and multiply by 6 in times. Oh, this is one of those that just keeps going. And so this is kind of more of an equation, which was where we're headed with this stuff. Because we have a base, we know what we're multiplying by, but we don't know how many times we're going to do that. Alright, so let's fill in the blank. We can use blank to represent repeated multiplication, and now we know that that answer is exponents. Alright, so just like addition has the inverse of subtraction, obviously multiplication has an inverse of division. And can we still use exponents if what we're trying to do is divide? And the answer, luckily, is yes, but it's a little bit more complicated. To divide by a number, it's the same thing as multiplying by its reciprocal, okay? Often, if it's just a plain number on the bottom, that means 1 over that number. Because remember, if x doesn't have a denominator, he's over 1. So then if we were to flip it or find the reciprocal, it would give us 1 over x. Okay, so let me try to explain this as well as I can. So when we look at this first example, it asks us to divide 1 by 6. All right, so whenever we're doing this with multiplication, if we're dividing 1 by 6, what I really want to do, and what the more complicated problems is what we're thinking ahead for here. Obviously that's not hard by itself, but we're going to take the top number and simply multiply by the reciprocal of this bottom number. So right now 6 is just 6 over 1. We don't write the over 1 because it's a whole number. But if we are going to flip it, I have to remember that part, because it's really the same as multiplying by 1 over 6. Okay, so let's do 25. It says start with 30 and divide by 3 2 times. So we're going to try to divide by 3 2 times. So instead of divide by 3, I'm going to multiply by 1 over 3. And I'm going to do that 2 times. Okay, and this is where exponents will still come into play for us. And so we can rewrite this as 30 times 1/3, and I'm just going to start using the parentheses here. You could use the little dot like we did here. Either way is fine. And we multiplied by 1/3 2 times. Okay. Number 26 says start with 80 and then divide by 5 10 times. So instead of divide by 5, I'm thinking of multiply by its reciprocal, which is 1 over 5. And okay, it's going to happen 10 times. Ooh, beautiful. So what we can do instead is write it as 80 times 1/5, which is the same as the divide by 5 part. And then the 10 times is just how many of these we have. Okay, I'm not going to draw those circles because I'm feeling lazy. But that's where we're going with that. And last but not least, start with 90 and divide by 10. That means multiply by 1 over 10 3 times. Okay, and so then we can simply rewrite this one as 90. Our base, what's repeatedly being multiplied, is 1 over 10. And we did that 3 times. Okay. And let's move on from here. So indicate whether the following situations can be represented by repeated addition or repeated multiplication. So number 28 says, your phone bill has a charge of $29.95 and an extra 10 cents per minute for the n minutes you went over your plan. Write an expression for the cost of your phone bill if you exceed your plan by n minutes. Okay, so we have our starting amount, $29.95. Okay, and let's say I'm going to talk for an extra 2 minutes. So if it's 10 cents per minute, that would be plus 0.10 and then plus another 0.10. So you can already see, just by thinking of a very simple scenario of like 2 extra minutes, that the way I'm calculating this is by adding on. So if you notice your pattern is adding, then that means that you're going to have, obviously, repeated addition. Okay, so for this one we're going to say it's repeated addition. We'll have another vocabulary word for this soon. Okay, this is just kind of getting it rolling here. Okay, but we don't know if it's for 2 extra minutes. It says for n minutes. So I'm just going to get rid of that guy. And since we know it's going to be repeated addition and that we represent that with multiplication, then for n minutes, we will simply multiply that number by n. I don't think it asked us to write the formula, but I think it helps put it together for us. All right, last but not least, you put the wrong soap in the dishwasher and strange things happen. That's a true statement. Your dishwasher started with 100 bubbles, and for n minutes, the number of bubbles tripled each minute. Write an expression. Oh, it does ask us to do that. For the number of bubbles in your dishwasher after n minutes. Okay, so we know we're starting with 100. So again, let's say we left it on for 2 extra minutes. So it would triple. Triple means times 3. Double means times 2. Quadruple means times 4. You really only hear those 3. So triple means times 3. That would be for 1 minute. This would be for 2 minutes. This would be for 3 minutes, and so on and so forth. Right? So what we're doing here is repeated multiplication, which means that our condensed formula will have exponents in it. So since we don't know the exact number of times we multiply by 3, I'm simply going to have a power of n, or an exponent of n. And this concludes our lesson for today. So now that you're finished with this, you can turn the page and start working on your pattern recognition, where you're identifying number patterns.